Hello again. It's the day after Boxing Day. Two simple videos sparked a lot of interesting debate and questions and answers and all kinds of stuff that I'd like to just explore very quickly. New t-shirt, got that for Christmas, look. So where do I start? I'm going to try and run through just a few points, not all of them, because you can read everything on the channel in the discussions. So, one thing that comes up all the time, without fail, is this one, which is, what data logger do you use? Well, that's it. That's Amazon. Now, $24.99, $28.99, $24.89, eBay £15 UK money, and you can also download the software. They give you, when you buy them, they give you a link to download the software to operate this, the hardware, if you like. So that's that one. Lots and lots and lots of clever stuff as well. I'm hoping you can read this on screen, because that is what someone wrote to me. The guy's name is Zachariah Heem, and this is all to do with nickel-ion batteries. Some stuff in there I didn't know, so I'll be looking at that when I get into my nickel-ion battery. Glad to see that Mr. Middleton is back in the fold again, big and bold, a wealth of knowledge and information, that guy, as I've said before. I did mention in the other video that he showed me that, or got for me, that formula for the CMC and the SBR, and he's also added to that now. Excuse me, and mentioned something that I sort of got the gist of this one when I was trialling CMC and SBR as a binder, which brings me into two areas really. The first area, we'll talk about the binder situation, because this is so important. If I can find a pen. Oh yeah, so important, this one. It's about your active material and your binders. If you've got a piece of active material with all its angulations and surface area, and its little canals of micropores, what's going to happen when you insert that carbon into your binder? Well, I'll tell you. All of those lovely little, well, apart from the fact that you're going to coat a lot of your outer surface with your binder, you're also going to fill those micropores. Like that. So basically what you're doing is you're just bunging the whole thing up. And it was in discussions with Pete a while back, I don't know, about 6 months back, something like that. I was trialling this method that he proposed, or the formulation I should say, and it worked great, you know, apart from this problem. And at the time I thought, there's only one way out of this. If it's an aqueous solution, an aqueous binder, then what you've got to do with that carbon is wet it first before you put it in the binder, or before you add the binder to it. And what's going to happen then is this you've still got all of your little micropores, your little canal network of surface area. But effectively, what you're going to do is this. Now this is a bit rubbish, I know, but I should have got one of those big thick marker pens, but I'm hoping you can see that. Those canals are now in red. That represents where you've just soaked your carbon in, let's say, water. Because it's aqueous, isn't it? An aqueous binder, so it's not going to hurt anything. And when you dry the whole system out, that water should evaporate or do what it does. And you'll end up with all of these canals, this network, this microporous structure intact. Okay, the outside, what do you do with the outside then? Because you're going to coat it, aren't you? Well, if you look at the processes with lithium ion batteries, let's say, they get these lovely foil strips and they coat the foil with the binder system and the carbon. Now, what do they do next? Well, they calendar it, don't they? Which means it goes through a roller process where this is what happens. That there is your aluminium foil. You've got to maintain contact with that carbon, which is going to be conductive. It's going to be a conductive carbon. Well, it should be. That's the best way. That's the best carbon you can get, is a conductive carbon. And they literally force that carbon into that foil. That's what happens. Now, it's such a thin layer that, you know, your electrolyte is going to be surrounding that anyway and going in these, all of these pores. To give you maximum contact, that's what's happening. So you should have a conductive electrolyte anyway. So you've got a full conductive path from that foil or your collector plate through the carbon, through your electrolyte. Ions can zip backwards and forwards quite easily, and the more that's coated, the more resistance you've got and the less surface area you've got. So that's it in a nutshell, really. So preparation again. I'm hoping that that's a pretty good explanation of what I've been trying to say. If you, in a nutshell, if you fill those micropores with your binder, you ain't going anywhere. It'll work, probably, but not very well. So, what's the next best thing then? The same piece of carbon with all of its surface angulations, nice little areas to store energy on, and you've got your little canals, just the same, your little microporous network. Now, once I'd got over the idea of wetting the carbons out, I then thought, well, what better could you wet the carbons out with than water? Electrolyte. Now I did that and it worked a lot better. What a good start for your battery, because you imagine all of your little microporous network now, not with water in it, but with electrolyte. So that's the little sort of debate there. Not a debate, but you know, I'm just trying to answer questions, aren't I? It was never a debate. It was just a thought process. So, while we're on the subject of activated carbon, I mentioned in my video that I've got some in my ball mill there, some regular activated carbon, coconut variety, and it's rubbish. So I'm further processing it because it's all that I'd got available at the time. As you know, the shelves are emptying by the day. Everything's gone in the bin, and I've ended up with a load of empty blackish tubs. And I've got to start again, and it's going to be a long process. So the kiln's not there, it's over there, and I'm getting on with it. Now I'm kind of 2/3 of the way around this place. Everything's moved over there, a lot of stuff's moved there. I've just got to finish that area there and I'm away. But back to activated carbon. A lot of people also ask me where I buy this very fine powdered activated carbon from. eBay, and it's called, the company's called Pura. I'm looking at the tub now. If you type in on your eBay search Pura and then coconut activated charcoal powder, you'll go straight to that. I bought the 2 kilogram tub because if you buy a small tub it's quite expensive, but if you buy a large tub it's extremely cheap and you get a lot of it. There is a lot, it's a big old tub that. So, you know, that's another one. Now, I also mentioned that with this stuff, this activated carbon charcoal coconut variety stuff that you buy in powdered form, what they've done is they've taken those big granules that you get in your fish tank and powdered it. Now that rang alarm bells at me because, you know, I was wondering why it's rubbish, and it is rubbish compared to any of my carbons. It's lost a lot of its activation in my view. Again, you've got to think of it in similar terms as what I mentioned earlier on with all your microporous structure. If you've got a big lump, let's say that lump is a house, it's your house. If you close all of the doors and the windows, you've just got your house. Got the roof, your walls, and that's it. And you've got all your lovely brickwork and your windows and your doors with all of these points which we could call surface areas with an S on the end. S. So what could be better than that then? So your house is that lump of carbon. Well, what could be better is if you opened all of the windows and all of the doors. So if you open a window, you've got access to a room with all of these other areas in the room that we can class or call a surface area. So there's a bit of a micropore there. So if you open all of the windows and all your front door, your back door, you've got tunnels, you've got hallways, staircase, landings, doors, access to all of these points which could be considered as surface area. So that's a good analogy, I think, really, isn't it? It's a good way of looking at it, because some people understand it and some people don't, and I get asked these questions all the time, and there have been a lot of questions asked about this activated carbon and why I think that this powdered stuff is no good. I mean, if you look at it like this, let's take one of those big lumps and cut it in half. And you had that area there as some surface area network, and then you smash it all up. You still end up with a lot of surface areas, but you lose your micropores, those areas. I feel that is what's going on, and you know, you can try and shoot me down in flames if you like, I don't mind, but I'll soon tell you, because once I start you know, firing my kiln up again. There's a important point there. I'm going to reprocess that carbon, which is now a lot finer than it was because it's gone through the ball mill with aluminum oxide balls, and they're working extremely well. So I don't want anyone else saying to me, well, you know, try this, try that stainless steel ball, because that's it, finished. No more stainless steel balls. You're always going to get in a nano form wear from the ball in your material, and that's even worse, isn't it? You know, nano form. But anyways, someone said, a while back you mentioned microwave and this is the way forward and all the rest of it. Well, it is and it ain't, because to me it is not controllable. Now, early this year I thought of a superb way of controlling the microwave and controlling the temperature in your pot in the microwave, and I intend to make a kit next year. This is one of the products I've been working on, a kit with a PID controller and all the rest of it to control the temperatures in a microwave. So that's another one to look out for in the new year. You know, he said, now you're talking about your kiln. Well, it's the best thing I've got, because I can control the temperature. You know, it's no good saying, well, you've got high, medium, low settings on a microwave. What good's that? You want a temperature. If you want to calcinate something at 650 degrees, you want to know that you've got 650 degrees for an hour or 2 hours. You know, that's what you need to know. So all sorts of interesting stuff came up on these two videos. I mentioned that I'd made some of this stuff. This one is probably the main sort of a debate, if you like, because I said I was going to message Rob, and I hope he doesn't think I'm being thick. But like I said, I'm not a chemist, am I? You know, I'm doing my best to get my head around all of this stuff. I did, you know, Wikipedia stuff first, and generally got on the internet to ascertain what a double displacement reaction is. Now, I've got the papers from Wikipedia. Got it here. If you look at double displacement reaction Wikipedia, it comes up with salt metathesis reaction, which is what it's often known as. It's sometimes called a double replacement reaction or a double displacement reaction, even a double decomposition reaction, which is a chemical process involving the exchange of bonds between two non-reacting chemical species, which result in the creation of products with similar or identical bonding affiliations. That's what it says. And then it gives you this general scheme. I should read on. The bond between the reacting species can be either ionic or covalent. Classically, these reactions result in the precipitation of one product. Now, this is the bit that kind of, I don't know what we've ended up with there classically. I just, you know, I'm trying to get my head around it. And this, right, okay, so this goes on to say the general scheme. Now, I understand this bit, you know. You start off with A and B plus C and D, okay, which then, after the reaction, ends up as this. So A and B and C and D have ended up as A and D plus C and B, although that should be B, right, like that, because this was the other bit I couldn't quite grasp. Anions, cations. Okay, we've swapped around there. The compounds have swapped around. But when we look at zinc and potassium, zinc is a 2+ metal, potassium is a +1. Oh, so 2 cations, in my view. Have they swapped to anions, or are they still cations? It's just a bit confusing for me. You know, yeah, I could do a lot of research, but I just sort of simply ask Rob the question, which I've done. I don't think he's answered it yet, but you know, it's holiday and all the rest of it, isn't it? You know, he's taking a break, you know, well-deserved break. So another paper which I read, well, not particularly a paper, it's just an explanation on the internet. What is a double replacement reaction, which is also described as a double displacement reaction. Double replacement reactions, also called double displacement, exchange or metathesis reactions occur when parts of 2 ionic compounds are exchanged, as in that, making 2 new compounds. So we've got 2 new compounds. The overall pattern of a double displacement, well, basically what I've just put there, you can think of the reaction as swapping the cations or the anions, but not swapping both, since you would end up with the same substance as you started with, obviously. So the solvent for a double replacement reaction is usually water, and reactants and products are usually ionic compounds, but they can also be acids or bases. I guess that's taking me back to cerium oxide being an oxide base, and I need to convert it with some acid, don't I, into a metal salt. So what else can I think of that was interesting? Bear with me. The water battery produced some questions, debates, answers, whatever. One good suggestion, of course, was that I use this stuff, and someone said that could be acidic. Although, you know, I did the litmus test all the way through. Now that's not, you know, 100% reliable, is it? I've got a digital pH tester somewhere, and I don't know where it is. But maybe with this big tidy up I'll find it. Same guy also said use urea in the water for various reasons. You can read all of this, obviously. Oh yeah, hey, that was it. Adding urea to the water will improve current due to carbon chain storage mechanism within the water. I kind of understand that. A lot of people also ask me, or say to me, that they can't find Gerhard's channel. Well, I've put a link in one of the questions, because that was one of the questions. For the life of me, I can't find Gerhard's channel. Now, he's spelled Gerhard, Gerhardts. There's no T on the end of it, it's just Gerhard ending with a D. So if you type in his name in, and you put a T on it, it's wrong, isn't it? So, and his channel is called Eco Kimalpi. I don't even know how you spell that, actually. Let's just try and find him. Okay, bear with me. Eco Kimalpi. Eho Kimalpi. EHOCHIMALPI. So there, that's Gerhard's channel. Interesting stuff, you know. But anyways, I'm listening to me going on my video here. Look. a lot from Peter Middleton. I suggest that everyone looks at his comments, because like I said, the guy is a wealth of knowledge and information. I'm trying to make this video not too long. There's 100 more things I could talk about, but I won't. All the comments are there for everyone to read. Peter Middleton, glad he's back in the fold. He did threaten earlier on in the year that he was possibly going to make a video at some time. To use one of his local expressions, get on with it, flower. Right, Pete? So anyways, I've had a good Christmas because I've been in here, which is where I love to be. It's, like I say, the day after Boxing Day now. Look forward to some stuff from me shortly now. I've got to get to grips with this place first. But, you know, once I've edited this video and uploaded it, I'm back in here and that'll be it. Where are we? You know, it's 2:30 afternoon, PM. So, obviously the comments just keep coming in, and there's no way I could keep up with them. So, you have a good one. I'm back because I need to explain something. When I was talking about that, a typical lithium-ion battery with a piece of aluminium foil, copper foil, which is there. And those little bumps are your lumps of carbon. I said you've got a nice conductive path. Now, when I say conductive, I mean electrically conductive. There's some nice conduction between your foil and your conductive carbon. So, good for electrons then. We know the electrons can travel through the foil, but where do they go then? Through your carbon, via a nice electrically conductive path. The other conductive path is an ionic conductive path, isn't it? Through your electrolyte as a pathway to those carbons. A pathway to all of that lovely surface area, that microporous structure. So I should have explained that. I have now. Now I was going to save a lot of this for next year, but because certain things have cropped up anyway, I'll start explaining things now. I can expand on what I've just said. That was aluminium strip or copper strip in a lithium-ion battery. That was a lump of carbon that's forced into the aluminium, i.e. calendared. Now, in previous videos a while back, Rob's videos, you would have seen way in the corner a little machine, a hand rolling machine, which is a calendering machine. I think I don't know, 6 months back, something like that in my videos. No, it would have been longer than that actually. In the corner there, you would have seen a big blue press. I looked at presses on eBay, they were phenomenal money, but all of a sudden I found a heated press, even better, with a tremendous amount of force on it, and you can set it, you know, your different levels of pressure, and it was £150. And you know what it was? It does this. It was a t-shirt printing press. To end up with a t-shirt with a picture on it like this, or text, or logos, you know, all that. So the reason for me buying that was, I all of a sudden realised we're using these binders that you spend a lot of time, effort and money producing a good carbon, or you buy one, and you end up with this. In the main, those lumps of carbon are surrounded by your binder. Now there's one lump there that's touching, look. So you've got to think about a conduction path. Where does it go after that? there's the problem. So I found that I wanted to experiment with thicker and thicker and thicker materials. You know, I got up to, I don't know, about 2-3 mil, something like that at the time, 1.5 mil, whichever. And then I found that when I increased it to sort of 2.53 mil, it was not that good. So this is why, when I were to press the materials, they were so much better. So you end up with all of these materials, i.e. your carbons, actually connecting and touching each other within the binder system. Yes, you've still got binder around them, we know that, but the more of those lumps of carbon you can get pressed together, the better. And that's what this you can call it a calendaring process if you like, but it's a press method. And once all of this is sort of, you know, operational, as I want it to be for next year, with my 2-roll mill situated on there, I'm going to get rid of my big sonicator there, which is like this big, and I'm going to put that roll mill there, and my press is going to come back into action and go back in the corner there. So hey ho, can't wait for the new year. This is never ending, isn't it? I just finished doing that last bit of video about this, and then I've got a message, my phone bleed, from Dennis over there in Michigan, and his comment was, apart from Happy New Year and all the rest of it, he says, my backlog of things to try on new cells and recipes is getting really long as I'm drinking from a fire hose of the knowledge that you've shared with us. Thank you. So I'm going to share some more. One thought on your comments on your array of current collector choices: why not use a very thin conductive layer of graphene that you overlay with a very high surface area carbon mix? Isn't that strange? I designed this about 6 months ago, which is a flexible sheet of graphite. Okay, there it is. This is a comparable size piece of 1 mil graphite sheet. Now if I put the two on the scales, firstly, my graphite sheet weighs 1.01 grams. Now I know it's had some wear because I've tested this in batteries, obviously. So there's some graphite missing from the surface, but let's say it weighed 1.5 grams. The graphite itself, which is 1 millimeter thick, 12.21 grams. Now, before I blow my own trumpet, we know that if we put a multimeter on that, it's going to be next to nothing in ohms. Well, I'll try it, shall I? Well, it says 0.7 ohms. Doesn't matter where you put the probes on the surface. And thinking of Dennis, he's just done a video and made a square probe, and he said, would you like me to send you some of these bits so you can make one? Well, I'd already 3D printed one. I've got a couple actually, I don't know where they are, but I should be using those now, shouldn't I? It's all in the new year. Now, what does this do then? Let's have a look. All I'm going to do is touch the probes on the surface, and if I can get 1 centimetre apart, I'm trying to do this like this. It never works, does it? I'll do it like this. I've got 7.8 ohms there, which isn't bad considering what it is. It was way better when I made it, and to be honest, I just put them on the shelf, thought yeah, that works, I'll get back to that again and make them better, obviously. Now it's all in a binder. The difference is if I were to put the probes either side of this and give it a little press, nothing dramatic, I'm not trying to force it through the material, well you can't force it through the material, we get, have I got a light on this? Oh yeah, we get 0.8, 0.9, press a little bit harder, 0.7 of an ohm. Now yes, this is an old cheap tack meter, but I've got a really good LCR meter there, and I know for a fact that if I get that out, it's going to agree with this 100%. So that's my material. It's graphite, and what I'll do in the new year, you can see that flexing. Okay, what I'll do is I'll show you how I made that. It's not particularly cheap, but I gotta tell you, it ain't nowhere near as expensive as graphite sheets, nowhere near. So I'll just test one more time across the surface. .1 ohms. At 50 millimeters, 13.6. And if I go right the way across the material, 22 ohms. So that was 100 mil apart there. Now then, is there a way that I can make that surface conduction even better? Well, yeah, there is. That piece of graphite, if I overlay this onto that graphite and do the test again, on the surface at 1 centimetre, that said 1.1 ohms. Now, you've got to bear in mind that I haven't done anything with this spectacularly in terms of making it better. .2 ohms. Now that's with it overlaid onto the graphite. Obviously we've got a nice conductive path going on with the graphite, or a better path, because we're conducting through my material, which if you remember was 0.7 of an ohm, 0.8, 0.9. We're conducting through the material, through the graphite. Now I'm not saying that I would use that graphite as a backing or a collector plate for my graphite composite sheet, but what I am saying is, if we can find a way to put a metal conductor as a collector plate with my material on top of that, because it's quite thin, we've got a nice conduction path through the material to the metal, which gives those 2 points less resistance. So I hope that I can improve on the product, and yes, this was all based on, I produced it in that heated press. So I feel that if I can produce a better binder system, that could be a fantastic product and a fantastic way out of finding a graphite plate. Now again, I was going to save all this till next year, but Dennis prompted me, it's his fault, sent me that message, and there we go. I'm not going to do any more now, that's it.